Hey guys, welcome to another video. So today's learning objective is to identify, describe and construct congruent and similar shapes, including on coordinate axes by considering rotation, reflection, translation and enlargement, including fractional and negative scale factors. And what this is kind of basically talking about is something we call transformations. And what we're doing is we're taking a shape and we're kind of transforming it, as it says in the name, into another shape. And with, say, rotation, reflection, and translation, we're left with the same shape, but kind of, maybe in a different position or a different orientation or something. And with enlargement, we're left with a similar shape, because we're enlarging it, kind of the angles and stuff will stay the same, and the ratio of the sides will be the same, but it will be larger or smaller. So it'd be similar, whereas congruent will be in rotation, reflection, and translation. So let's go through each of these in turn. First off, we'll start with rotation. If I move down here to a triangle I've got drawn out, if we have something like this, right? If you think about this triangle, we have to think about what rotation is, right? And I think that's something most people have a fairly good idea of. But if you think about it, if I use this tool, we can see what rotation is, right? We're kind of, I guess, I don't know how else to describe it besides rotating, but kind of moving it around, right? But what's crucial is that we rotate stuff around a point. So what I like to do is, think of is if you have a piece of paper out, right? So if I tear out a piece of paper, and if you have a piece of paper and you have a table, right? So stick this on the table, and then if you press firmly, and you can try like rotating around the pen, and you can see how you'd rotate around the pen, right? And if you draw a few shapes around on this piece of paper, you can see how kind of varying the distance from the pen will, I guess, make the shape, the rotation be a bit different depending. So if you draw a shape kind of on the top left and then rotate it clockwise, that will kind of, and then you compare that to right, having a shape on the top right and then rotating it. That's quite a good way of getting an intuitive idea of what rotation is, and really good practice, I think, of just rotating a few shapes, or with sticking your pen on. And basically, when it comes to kind of this mathematical rotation, it's very much the same principle. So kind of we look at this point and we think about, if we stick a pen here and then, shift that whole paper, where's point A going to end up at if we were to rotate this, say, 90 degrees clockwise, which is what's done here. So what's, again, really important is we need to specify where we're going to rotate about. A lot of the time that's the origin, but if they're feeling a bit, mean, they could do it, around this point, for example, or also rotate around this point. So if you think about, the way I like to do is kind of break it up into the y and x coordinates and see where each of those would end up at. So we look at point A, right? That's at 1, 1. Let's look at where the x coordinate would end up at after a 90 degrees clockwise rotation. Well, if this is here, we're going to rotate this 90 degrees to end up at -1. So one of the points that this coordinate is not going to be -1. And if we look at kind of 1, if we rotate that, that will end up at 1, right? But at x. So it's going to be, there's going to be a point at 1 and not -1. So that's what A dash is. If we try that with C, or actually with B even, there's 3 here and 1. So we rotate this 90 degrees clockwise, the 3 will end up here at -3. That'll be one of the points. So perhaps if I use some colors, it will help. And if we look at the point 1, because it's 3, 1, right? So there's 1 here. If we look at the y coordinate, if we rotate this, that will end up over here. So kind of we look at where those intersect. And that's where B is. And again, using the same principle with C. And that's basically what rotation is. If you kind of struggle to visualize it straight away with the whole shape, try rotating point by point and then joining the shapes up, which is what I do kind of when I'm struggling with kind of thinking about how the shape would rotate. Sometimes they kind of provide you with tracing paper, and if you have tracing paper, your life is so much easier. What you do is you kind of draw the shape out, stick your pen at D, and then just, at the origin, which that should be O, not D, and then just literally try and pull the paper around to see where it would end up at. So if you have tracing paper, your life is so much easier. But if you don't, I guess that's how you approach it. So when it comes to rotations, there's 3 things if you want to describe a rotation, there's 3 things you need to specify. You need to specify kind of what angle you're rotating it by. So in this case, you're rotating it by 90 degrees. What direction, clockwise or anti-clockwise. And the third thing is about which point. So this rotation, if we were to describe it, we'd say rotate, so you obviously have to specify what transformation it is as well. Rotate 90 degrees, the angle, clockwise, about the origin. And these are kind of the words you need. If you're describing, you should describe it in that form. The other thing, I'm going to do translation first. It's really, it's worthwhile checking out the video on vectors, which is, a few down the line. But it's important to check those out to see kind of what how the vectors that you translate by vector. So to know what vector is, so please check that out. So you'll have to skip forward a bit, but I'll just in that I describe what a vector is. And translation just means moving the shape from one place to another by kind of a certain amount. So if you were to translate by the vector, say 2, 1, that means every point that you're concerned with, you move 2 to the right, and then or positive 2 in the x-axis, and 1 in the y direction. So if we look at A, if we want to move that to 1, we go 1, 2, and then not 1. So A, A dash dash will end up here, because that's the second. This is A dash, so this is A dash dash. Yeah, in general, with notation with transformations and stuff, we use kind of dash to represent kind of the new or transformed point. And same thing with B. Kind of, we know we'll go 2 to the right, 1, 2, and then 1 up. So B dash dash. And then same thing with C, 2 to the right, and 1 up. So C dash dash, and then we've got our shape. And if anything, you could actually just translate just A, and you can kind of just do it from there. If you know A is here, and then kind of B is too long, and then C is too up, like that, rather than kind of doing those individually. If you can kind of see that a bit more easily with translations. So you can kind of translate a shape way easier than say rotate, at least in my opinion. So that's how you deal with translations. It's again, you have to say translate by the vector, so you need the information of what the vector is. And then you've got reflections. So what you do is you reflect in a line, for example. So if we say we want to reflect in the y-axis, the original shape we have, what we do is we kind of think about the distance from the line, or the perpendicular distance from the line to the point. So if it's kind of 1 in this direction, then when we reflect, it will be kind of the opposite. So we'll go 1 in the opposite direction. So A dash 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 will end up here. If we do B, this is 3 away in the going right. So that's a perpendicular distance 3 away. So we have to go 3 away in the opposite direction. So 1, 2, 3. E dash dash. And then C, again, we use the same principle. It's 3 away. So looking at perpendicular distance 3 away, we'll end up here. So C dash dash dash. And we just kind of line those up. And also in general, when you do these transformations, do label these kind of A, B, C, just to know kind of the orientation there. So with this, the way you might want to think about it is if you stick a mirror along kind of the line, and then looking at what it would end up, the shape ends up looking like in your mirror. So if you have some sort of handheld mirror, or maybe you might be able to use your phone or something, or anything that's reflected, try that out. Sometimes the question's a bit harder because you have to reflect along, say, y equals x. So let me just make some space now. Okay. Okay. So if you were to reflect instead of along the y-axis, which is a fairly straightforward one because you just have to go like, it's in this direction, so you go like that. If you say in the line y equals x, which would be this line. So to reflect A, well, A is already on the line. So if you reflect a point on the line, if you kind of stick the mirror along this, that will stay in the same place, right? And the same thing with C. With B, remember we have to look at perpendicular distance. So we look at this perpendicular thing. It's kind of, like this, I guess, across one of these squares. So perpendicularly, if we go like this, then we can go up here. So this is where B ends up at. So B dash. This will be A dash. So we'll actually label that A dash. And then C dash here. And then we can kind of join them up. And as you can actually see that the orientation of the shape has kind of changed. So this would, you've got A, B, C like this, right? But now it's kind of going in the other direction, I guess, if you know what I'm trying to say. It's like so with this as well, look, the orientation has changed. Like you've got kind of A's up here now, C, ABC, and instead of having ABC like this, right, because it's rotated. And same thing here, so it's kind of facing the different direction. And if you had kind of even our other reflections, you had the orientation changing. And so we've done rotation, reflection. So yeah, so with reflection, you have to say along which line. So you say reflection along the line y equals x. Sorry, not along the line, in the line, that's the wording. So you do reflection in the line y equals x, for example. So again, in general, when it comes to reflection, just think about the perpendicular distance to the line, and then just kind of follow it along the other way. So maybe if we were to do an even harder one, if we just to solidify, I guess, the thing, we're doing a reflection in y equals minus x, which is this line here. So again, we think about perpendicular distance. So to A, perpendicular is like this. So you go perpendicular again to out here. So minus 1. This is A dash. We look at C, again perpendicular. So this is 1, 2, 3. So 1, 2, 3. So this is where C dash ends up. If we look at B, again perpendicular. So we go, again, we wouldn't go to the origin here, we'd go to this point here. So this is 1, 2. So 1, 2. And you can kind of see that the shape looks the same at least. So you still got a triangle, right? You shouldn't somehow expect it to be distorted more than that. I mean, if you somehow got B ending up here, you'd be, sorry, B dash ending up here, you'd be like, whoa, what's happening here? It's no longer a right angle triangle, right? So, you should watch out for that kind of stuff when you're doing these transformations. The shape should stay the same. And the final thing is what we call enlargement. And kind of, as the name suggests, you're, literally just enlarging it. But the crucial thing with enlargement, again, is you have to think about it kind of, so with the scale factor, so by what factor are you enlarging it by, and kind of about what point. So, if you were, say, enlarging the shape around about the origin, so you think about kind of enlargement from which point. So if you have it, if say we were enlarging from the origin by a factor of, say, 2, so we look at where A is. We can maybe, it's better if you have a ruler. You can draw kind of a line from A. I think so. If this length here is 1, we have to extend this line such that if it's a factor of 2, then the line is now twice of what it used to be. So you're basically taking this line here and just stretching it out by the factor you need. So if A was here initially, that's what the original line was. Maybe if I do this in red, this is the original line up to here. You now create a new line, which is twice the length, but in kind of the same direction, of course. So which will end up here. So A dash is over here. With C, it's actually not even going to fit on the page because it's a factor of 2. So look, C was all the way up here at 3, 3. Kind of go like that. And then now we have to go twice the distance. So this is 1, 2, 3. So it will be up here at 6, 6. So I'll just So if you draw it, what's that, 1? I'm guessing 6, 6 somewhere up here. So this is C dash. And then again with B, if we look at kind of line here, so this is kind of, we have to double this distance. So you can see it goes along 3 and then up 1. So we're doubling the distance, so we'll go along 3 again and then up 1 here again. So B will end up over here. Is that 3? Yeah, 3, yeah. So at 6, 2. So sorry, C dash will be somewhat closer here actually than C dash, not there. Or maybe even here actually, sorry. Okay, and then you can just join them up as usual. So A dash is here. C dash. And then A dash. And there you go, that's your new shape. So it's important, so basically it's kind of like almost the shadow of the shape, that's how I like to think of it. So that you've got a bright source here, you know, and then you think about what the, I guess the shadow of the shape will be like if within a certain kind of scale factor, I guess. So, and of course, if you've done it by kind of, you've enlarged the kind of, yeah, so kind of, you might want to think about what the area, how the area changes as well. Because you've kind of enlarged kind of each point by a factor of 2, then the area would be 4. So if you kind of don't really believe me, you look, this is 2 wide by 2 high, so the area is 2, half times 2 times 2. And here this is 2, 4, this is 2, 4, right? So a half times 4 times 4, which is 8. So 16 divided by 2, if anything. So you can see how the area, you know, if it's scale factor of 2, then the area scale. So you will think about what the length scale factor here is. We're increasing kind of the length of each point by a factor of 2. So we'll increase the area by a factor of 4. So kind of 2 squared. And then there's also stuff called, you know, negative scale factors, as it's mentioned here. And that just means going in the opposite direction. So, you know, usually you go to the point and then kind of, you know, increase the length. So if you increase the length by 2 here, well, you take this line here and then you kind of stretch out so that it's 2. But if you think about what minus 2 would be kind of going in the opposite direction. So if you take, you know, you consider this red line and you go, okay, this is a factor of minus 1, and now minus 2 all the way is out here, like there. So minus 2 is just in the opposite direction. And fractional indices, again, it's the same principle. So you extend the line by, say, 1.5, for example. So that would end up somewhere here. And you use that same principle of kind of that, where it would, of taking that line and just stretching it out by the factor you're concerned with. Again, so, you know, it doesn't always have to be around from the origin. Sometimes you might do it, say, from this point here, or whatever point. In that case, that does make your life a bit harder. But it's the same principle. Just draw kind of a line from the place you're enlarging from to the thing, to your point, and then just stretch it out again by the factor you're concerned with. Well, another thing, you know, you might actually this is a bit of a, depending on how easy it is for you to visualize. If you struggle with visualization, as I did a lot, you know, this is a bit of a trick in the sense that if you're enlarging, say, you know, 1, 1 about the origin, it ends up at 2, 2, right? Sorry, by a scale factor of 2, right? And because that's kind of, you know, if you think about what 1, 1 is, it's kind of this here and this here, right? And you can kind of stretch each by 2, so it goes up here and here, and it ends up at kind of the intersection of those two, so 2, 2. So if in general, like, you know, you're doing it around the origin, you can just think wherever the coordinates are and then times them by the scale factor. So if you have b at, you know, if it's from the origin, you're enlarging, say, by a factor of 5, where does coordinate b end up? Well, you just go 5, basically. You know, you can't really times by 3, 1, but you times each of these by 5, so you get 15, 5. And even you can actually apply this principle from kind of, say, if it was enlarging from this point here, you think about, okay, so this is 2 this way, and if you're enlarging by a factor of, say, you know, 2 again, sorry, by a factor of 2, so this is 2 this way, well, now you're going to go double that way, right? So that will be 4. So if it was 2 away initially, now it's going to be 4 away in this plane, in kind of the, if point B, sorry, we're concerned. So that will end up over here, right? And if we're looking at C, well, that's 2 up and 2 to the left, right? Well, now that will be 4 up and 4 to the left. So we'll end up at, you know, over here, basically. So that's how you might want to think about it as well. And with enlargements, you have to say it's an enlargement by what scale factor and about which point. About a point. So not about, from is the word, not about. So that's how you kind of deal with transformations. I'll walk through some worked examples here to kind of when we have to describe transformations instead of performing them. Transformation that maps triangle A onto triangle B. So in this case, you know, it's pretty obvious it's an enlargement, right? We can see that, you know, they look the same, but B's a bit bigger, right? So it's clearly been somehow moved, right? So, you know, you could talk about this as multiple transformation, right? You could think about, oh, it's enlarged about the origin and then translate it. But this offers a single transformation, so you have to give it in kind of clearly one enlargement, because enlargement is the only thing that will kind of change the area and the size of the shape. So if we want to think about enlargement, we can kind of go, okay, so if we kind of, what I like to do is connect these dots, and then if you kind of connect all of them, actually, you'll see where kind of they'll intersect at the point at which they've been enlarged at. So, if anything, maybe if I use one of these straight line tools. Oh god, I don't know why it decides to do that all the time. Of course, you know, if you use a ruler, your life would be a lot easier. So, I'm not sure, okay, is that this? There we go. Okay. So basically, you just kind of connect the relevant points, that I guess the corresponding points, maybe that's a better word. So you know, this point clearly corresponds with this point, and that one with that, and you'll see kind of where all the lines meet. So again, if you do it with, you know, you only technically have to do it with two lines, and you know that they meet at this point, so you know that's where the enlargement will be kind of about. But not about, sorry, from, but I like to do it with all lines anyways, just to be sure. And yeah, so look, all the lines meet here. And now you know all the lines meet here, kind of this is what I was talking about with the shadow, and imagine some sort of light sources over here. So if you want to consider kind of the scale factor, what you'll do is now kind of think, what's the length here, and what's the length here now? So if I maybe, what's this big length here, and this small length here, and consider the ratio of those two lengths. So that looks kind of double to me. You can check. So this is 6. What is that? 1. So what is that? So 5, and then 5 again, and then you know, what is that? What is that? 4 up, 4 again. Yeah. So that's clearly a scale factor of 2, and it's from this point 6 minus 7. So you say enlargement from by scale factor first. By scale factor 2 from 6 minus 7, and that's how you do something like that. So of course, use a ruler, your life will be a lot easier. And also, if you really want to confirm it, what you can do is you can say, well, find the area of this and find the area of that, and then you should know that should be, say, if it's a scale factor of 2, then the area scale factor should be 2 squared, so that's 4. So that's a quick way to check. We've got another question as well. These are kind of when you have two transformations. So shape A is transformed to shape B by the reflection in the x-axis followed by translation PQ. Find the value of the shape PQ. Find the value of P and the value of Q. So in this case, what we have to do ourselves is actually translate it in the x-axis, and then we can figure out what the following translation was. So let's reflect this in the x-axis, which is actually a fairly straightforward thing. Again, I like to do it point by point. So if you look at it, you know, this is 2 up, so this will be 2 down. So over here, again 2 up, 2 down. What is this? 4 up, so 4 down. 4 up, 4 down, and we've got it like so. And you know, we might want to call this a dash, maybe not a dash. I don't know. Say call this R for reflected, and it's gone from this to here. So if if you just consider one point, you can see what the translation's like. If you think about this point clearly ends up with this point. That's the only way really a translation can work. You know, you're picking up and moving it along. So, you know, you haven't flipped it or anything, so, you know, this point couldn't end up with this point, because, you know, that wouldn't make any sense unless you'd flipped it somehow. So you just kind of think, okay, so this is going 1, 2, 3, 4, 5 to the left. So that's P is going to be minus 5. It's going 5 in negative x direction, so minus 5. And Q, so it's going up 1, so Q is 1. So 1 in the positive y direction, and that's your answer. So that's how you do the questions such as these. So again, with transformations, if these are the first time you've seen stuff like this, you know, it's really important to just practice it loads of times, because I knew I struggled so much with transformations till I did loads and loads of questions. And the more you kind of visualize the transformation yourself, the better you get at it. So what I like to do is, if you can go on GeoGebra, it's a good website where you can actually visualize these transformations yourself. And kind of the more you do, especially with weirder shapes, you'll get a better idea. So when you see a shape, it will be easier for you to, you know, rotate or reflect, etc. The hardest ones I personally found were rotation, and again, that tracing paper trick really does the job. So yeah, hopefully that all made sense, and I'll see you guys in the next video.